Welcome to Physics Hub. Today we are going to discuss a very important topic from classical mechanics, special theory of relativity. Now, as you know that in each and every exams of physics like IIT JAM, NET, GATE, JEST or TIFR, one question definitely comes from this particular section, special theory of relativity. So this topic is very important in your exam purpose. Your NET exam is over now. So our main focus will be on GATE, JEST and IIT JAM. Now the syllabus of GATE is very huge and I cannot cover all the topics from GATE exam syllabus. So I will cover only those topics which are important or questions generally comes from those topics or those topics which are little tricky. Now as you know, I posted some vote or poll in our community post and I gave 3 suggestions which ones we should start first. First one was time independent perturbation theory, then special theory of relativity and then superconductivity. Now most of the people chose special theory of relativity. That's why we are starting with special theory of relativity. Now as for the today's videos is concerned, I have divided this video into 5 topics. First one is inertial and non-inertial frames. Secondly, postulates of special theory of relativity. Thirdly, Galilean transformation. Fourth, Lorentz transformation. Fifth, consequences of Lorentz transformation with some solved examples. Now let's start with the first one, inertial and non-inertial frames. Now to understand the topics of special theory of relativity, we must know what is an inertial frame and what is a non-inertial frame. So let's start that. Before going to inertial frame, let's discuss about non-inertial frame, which will help us to understand inertial frame. So any accelerated frame is called non-inertial frame. It may be any accelerated train or merry-go-round. These are all accelerated frames or non-inertial frame. Now in contrary, any unaccelerated frame is called inertial frame. Okay, unaccelerated means if we consider any particle in that particular frame and until and unless any force is acted on that particular particle, it will remain in the state of rest or in uniform motion. Okay, so this is the same thing you have seen in Newton's laws of inertia, in Newton's first law, that if no force is acted upon any particle, then the particle will remain in either in the state of rest or in uniform motion. Okay, now we'll do the further discussion on special theory of relativity taking only inertial frames. We'll not consider any non-inertial frames. So you have got the idea about the inertial frame and non-inertial frames. Now moving on, let's talk about the postulates of special theory of relativity. There are 2 postulates of special theory of relativity. The first postulate says the laws of physics are the same in all inertial frames, and the second one is the speed of light c in free space has the same value for all inertial frames. So these 2 postulates must be obeyed in all the inertial frames. Now after this we should talk about Galilean transformation. Now as you know that in case of Newtonian mechanics, space and time are completely separable and they are connected by Galilean transformation. But as far as Newton's laws are concerned, it works fine, but it miserably failed in case of electrodynamics. That's why we need Lorentz transformation to tackle the cases of electrodynamics. But for the time being, we should know about Galilean transformation. What is Galilean transformation and why did we require some other transformation to tackle all the cases other than Newtonian mechanics. So to understand Galilean transformation, we consider two frames. Suppose this frame is S frame, and this is x-axis, this is y-axis, and this is z-axis. So look, in different time you have seen that the x, y, and z-axis are chosen in some fashion. But remember one thing: if you rotate in xy direction, it should give the direction of z. It always follow the right hand rule direction. Okay, so if we are moving in this way, then it go forward. So look, this is x-axis, this is y-axis, and if you are rotating the xy axis in this way, then you see that it will forward in this z direction. And in this way you can select the coordinate x, y, and z. So this is S frame, and we are considering another frame S prime, which is moving with some velocity v along x-axis, and we are calling the axis of that frame as x prime, y prime, and z prime, and we are calling this frame to be S prime. Fine. Now we are considering a point P, some point P. So with respect to this unprimed frame, means S frame, the coordinates will be written like this: x, y, z, and time t. And with respect to this frame, S prime frame, the same point coordinates will be written by x prime, y prime, z prime, and t. Okay. So according to Galilean transformation, time, or let's write for the timing t prime. Now Galilean transformation connects these two things. Now how does they connect? The transformation rule is given by this. So these are the called Galilean transformation: x prime equal to x minus v into t. This is the velocity with which this frame is moving with respect to this S frame. And y prime does not change, z prime as well does not change, and according to this transformation, this time is same in all inertial frames. Okay, and we can also write the inverse transformation, means x equal to x prime, and only what will happen, minus v will become minus v, so it becomes plus v, and y becomes y prime, z becomes z prime, and t becomes t prime. So this transformation is called Galilean transformation, and this transformation is called inverse Galilean transformation. So this is called Galilean transformation, and this is called inverse Galilean transformation. Now the question is, why should we introduce another transformation when we have this Galilean transformation? Let's look at that case. So we know this, so let's take an example. So what we are doing, these are coordinates. Now we are trying to find out the velocity. So in general term, we can write r equals to, or r prime equals to r minus dt. Okay, this is the coordinate. Now if you want to write the velocity, then what you can write, u prime equals to u minus v. This is in terms of velocity. And further, if you want to write the acceleration, we have to take the derivative with respect to 2 once more. So a, now v is constant, so a prime becomes a. So as you can see, acceleration in both the frames are equal. So these two frames are inertial frames because acceleration is equal. So there is no relative motion between them, means this prime frame is not accelerating with respect to this frame because they have the same acceleration. So they both are inertial frame with respect to each other. Now what is the problem of this Galilean transformation? Let's suppose we choose, look, so this we get from this relationship, and if we apply the inverse transformation, similarly we can get r equals to r prime plus dt, and we get v u equals to u prime plus v. Now let's suppose u prime is c, velocity of light. If some particle is moving with some relativistic velocity, let's say that with the velocity of light, then if we choose u prime equals to c, then u becomes greater than c. But as you know, from the second postulate of special theory of relativity, the speed of light in free space has the same value for all inertial frame, but we see that it doesn't hold here. That's why we need another transformation to tackle this situation. Now let's talk about Lorentz transformation. So to discuss Lorentz transformation, we took the same example. So one frame S, this frame S is called unprime frame, and as there is a prime, so it is called prime frame. Prime frame moves with respect to unprime frame. So x, y, z, this is prime frame, and with respect to this, an unprime frame, prime frame is moving with respect to this frame with some velocity v, and for the point P, these are the coordinates with respect to prime frame and unprime frame. Now how they are related is given by this Lorentz transformation. So how x is related, x prime equals to gamma into x minus bt. In case of Galilean transformation, only x minus bt part was there, but there was no multiplicative number. But here we get a multiplicative number gamma, and where gamma is given by, so right here, gamma equals to 1 by root over 1 minus b square by c square. Now what is the range of this value gamma? Gamma is always greater than 1, greater or equal to 1, less or equal to infinity. Okay, so gamma can have this type of value, not equal. It will always greater than 1, less than or equal to infinity. It should not write equal. 1 less than gamma less than infinity. Now if the particle is at rest, then it may become equal to 1. So this is for the x coordinate transformation in Lorentz transformation. Now what about y? Y prime will remain same as we have observed in case of Galilean transformation. Z prime will also remain same, but here in this transformation time is not invariant. Time varies with respect to frames. So t prime into gamma into t minus b by c square into x. So these transformations are called Lorentz transformation. Now as you have seen in case of Galilean transformation, it will also correspond some inverse Lorentz transformation. Any kind of Lorentz transformation must have its inverse transformation, otherwise you cannot say that a Lorentz transformation. So this Lorentz transformation is given when this frame, a prime frame, is moving in the x-axis with respect to this unprime frame. Now what about the inverse Lorentz transformation? For inverse Lorentz transformation, the negative sign will be transformed into positive sign. So x will be equals to gamma into x plus bt, x prime plus b t prime. Then y will be remain same, y prime, z prime. So as you can see, the dimension, that means the coordinate, is changing along that direction only in which the frame is moving. So the frame is moving in x direction, so only the x coordinates are getting changed, but the perpendicular coordinates, means y coordinate or z coordinate, they are not changing. Okay, now if the frame moves along y axis, then only y coordinate will change, but the z coordinate and x coordinate will not change. Okay, and what about time? Time equals to gamma t prime plus b by c square into x prime. So these transformations are called inverse Lorentz transformation. Now next what we'll try to do, we'll try to write this transformation in terms of 4 vectors. So what is 4 vector? Let's talk about how can we write 4 vectors. I'm not rubbing this part. So in case of 4 vector, we write for the time coordinate, we write it at x0. Okay, for x coordinate x1, for y coordinate we write x2, and for z coordinate we write x3. Okay, so these are the 4 coordinates in unprime frame, and in the same in the prime frame it is written at x0 prime, x1 prime, x2 prime, x3 prime. Now how they are related? To define the relationship, we just write x0 x0 equals to c into t. Along with it, we are introducing another quantity beta, which is equals to v by c. Now we are trying to write this transformation in terms of these 4 vectors. So how can we write? Let's suppose we are writing for x0 prime. So just multiply both the side with c. So ct prime. So as I have told, x0 equals to ct. So ct prime will be x0 prime, and gamma will remain as it is, gamma, and c into t means x0 minus, now we are multiplying with c, so one c will get cancelled, v by c we have written beta and x, and as I told, x1 means x, this is equivalent to x, this is equivalent to y, this is equivalent to z, and this is equivalent to ct. Okay, now you can understand easily. So in place of x, what we will write? x1, beta x1, and x1 prime, how can I write? x1 prime means this, so gamma into x1 minus bt. We have to write b in terms of beta, so b means beta into c into t. Now ct equals to x0, so beta x0. Understood? Next, x2 prime will remain as usual, x2, and x3 prime is x3. Now what we are trying to do, we are trying to write this transformation in matrix form. Okay, so if we write this transformation in matrix form, then how will it look like? One thing I would like to tell you here, that beta will get value between 0 to 1. Okay, and the gamma they told earlier, gamma got this value. This is actually very important, these two things you should note it down. Now how can we write these things in matrix form? So we can write it like this: x0 prime, x1 prime, x2 prime, x3 prime equals to gamma minus beta gamma minus beta gamma, gamma 0 0 0 0 1 0 1, and rest of the thing will remain 0 into what we can write x0, x1, x2, x3. So you can cross check it. What it will produce if you take x0 prime, gamma x0 minus beta gamma x1, and x1 prime will produce minus beta gamma x0 plus gamma x1. Okay, and x2 prime will produce x2, and x3 prime will produce x3, and this matrix is called Lorentz Transformation matrix. Fine. So this is the Lorentz Transformation matrix when the prime frame is moving along the x-axis. Now suppose the prime frame is moving along the y-axis, then what will be the Lorentz Transformation matrix? So when the primed frame is moving along y-axis. So in place of x-axis, it is moving now along y-axis with the same velocity v. Then what will be the Lorentz transformation matrix? Suppose we are writing the Lorentz transformation matrix as gamma. Okay. So this is when the prime frame is moving with respect to x in the direction of x-axis. Now when it is moving along y-axis, then this Lorentz transformation matrix is transformed according to this. So what we will write? Gamma, then 0 minus beta gamma, then this gamma comes here, this minus beta gamma will come here, and 1 will come here, 0, 0, 0. This will also be 0, and in the fourth place, as usual, it is 1, and the other terms will be 0. Okay, so this will be the transformation matrix. Maybe it is not visible from the board, so I am writing it here. So the Lorentz transformation matrix, when the prime frame is moving along the y-axis, it is given by gamma y. I am writing it again. Gamma 0 minus beta gamma 0, 0, 1, 0, 0 minus beta gamma 0 plus gamma 0, 0, 0 and 0 mixed here, 0, 1. So this is the Lorentz transformation matrix when the prime frame is moving along the y-axis with the velocity v. Now let's discuss some of the consequences of Lorentz transformation. The first consequence we are going to discuss is the length contraction. So what is the statement? Let's look at the statement. A rod placed in moving frame S prime appears to be contracted by the factor root over 1 minus b square by c square to a stationary observer in S. So to understand this, we are considering the same thing. We are considering an inertial frame S and another inertial frame S prime, which is moving with respect to velocity v. Okay. Now let's consider some rod. This is the rod, and this coordinate is x1 prime, this is x2 prime. Now one term is there, proper length. Proper, whenever you see the term proper, means that particular quantity is measured in rest frame. Proper time means time measured in rest frame. Proper length means length measured in rest frame. Now this rod is placed in the prime frame. Okay, so what will be the proper length of this rod? Suppose the proper length of this rod is L0, which will be equals to x2 prime minus x1 prime. Okay. Now let's suppose the length which is in S frame is given by L. Now what will be L? In L it will be given by x2 minus x1. x2 prime minus x1 prime. This can be written as gamma into x2 minus vt, and minus x1 prime means gamma into x1 minus vt. Therefore we can write this is equal to gamma into x2 minus x1, and x2 minus x1 is L, so gamma into L. Therefore with respect to a rest frame S, L equals to 1 by gamma, so L naught divided by gamma. So L equals to L naught by gamma, that means it is equals to 1 minus b square by c square into L naught. So as we can see, this term is less than 1, means this right hand term is less than L naught. So the length of the rod has been contracted. This is called Lorentz contraction, length contraction. Now let's solve some problem based on this. So this is the problem which is based on length contraction. The problem says so that if V naught is the rest volume of a cube of side L naught, then V naught into 1 minus beta square to the power half is the volume viewed from a reference frame moving with uniform velocity v in a direction parallel to an edge of the cube. So let's consider the cube. Let's draw the cube first, and we'll check what you will get. So suppose we are drawing the cube. So this is the cube and it is placed in S prime frame. Okay, and this frame is moving with respect to B, and with respect in some frame S, an observer and a stationary observer is moving this cube moving along some axis. Let's suppose this cube is moving along x axis. Okay, so in the rest frame, what is the volume of this cube? So in the rest frame, the volume of the cube is V naught, means V naught equals to L cube. If the side length is L, then the volume in the rest frame is V naught in the frame where it is at rest. So V naught is the rest volume of the cube of side length L naught. Then what will be the volume with respect to some viewer which is moving with uniform velocity v in a direction parallel to an edge? Okay, so this volume with respect to the rest frame. Now what will be the volume with respect to the prime frame? So as you can see, as I have told, the length gets contracted only along that direction in which the body is moving. So as it is moving along x-axis, so only the x-axis length will get contracted, but the y-axis and z-axis length will not contract. So suppose we are calling it V naught prime, the change volume, then L becomes, this 2L remains same, so L square, but this L gets contracted by L into 1 minus V square by C square. Fine, that is equals to L cube into 1 minus V square by C square. Now as I have told, V by C is beta, so L cube is given by V naught, so V naught into root over 1 minus beta square, and hence it is proved that the change volume with respect to the moving frame will be V naught into root over 1 minus beta square. So in this way we can utilize the concept of length contraction. Next we will be discussing about time dilation. Let's discuss the another consequence of Lorentz transformation, that is time dilation. So what is time dilation? To an observer at rest, a moving clock will appear to go slow. To understand this, we consider two frames, S and S prime. Now let's suppose that two different events T1 and T2 prime is occurring at the same position x prime. Okay, then the interval between these two events in the prime frame is given by delta T naught. Okay, T naught delta T naught is the proper time interval between these two time T2 prime minus T1 prime. Now the clock is in this frame, S prime frame, so it is at rest with respect to this S prime frame. So delta T naught is a proper time with respect to this S frame. Now what will be the time interval with respect to this S frame? Let's suppose that is delta T. So delta T is T2 minus T1. Okay. Now T2 equals to gamma into T2 prime minus plus v by c square into x prime minus, sorry, it should be right, t1. T1 is gamma into T1 prime plus v by c square into x prime. Okay, as we are considering the same point, we are considering two events at the same point, so we are writing x prime on both places. Okay, therefore it is equals to gamma into t2 prime minus t1 prime, and these two terms get cancelled out. Therefore t2 prime minus t1 prime is the proper time interval delta t naught equals to delta t by gamma. So this is called time dilation because delta t is with respect to this frame. Now gamma into delta t naught, is gamma is greater than 1, so it is the delay of time. That's why it is called time dilation. Now let's look at some example on this. A mason has a speed 0.8 c relative to the ground. Let's suppose this is ground. Find how far the mason travels relative to the ground if its speed remains constant and the time of its flight relative to the system in which it is at rest is 2 into 10 to the minus 8 second. So the proper time interval is 2 into 10 to the power minus 8 second. Okay, so let's discuss the solution of this problem. Okay, so as you know, the proper time interval delta t naught equals to delta t by gamma. Therefore, delta t equals to 1 by root over 1 minus b square by c square into delta t naught. Now this proper time interval is given, which is with respect to the rest frame, 2 into 10 to the power minus 8 second. And what is the velocity with respect to which it is moving? 0.8. So 0.8 c whole square divided by c square. And if you calculate it, you will get the value of 3.33 into 10 to the power minus 8 second. Okay. Therefore, the distance traveled by the mason with respect to ground is equals to v into delta t, because the delta t is the time interval with respect to ground and v is the velocity, the constant velocity with which this mason is moving. So v into delta t, so v is given to be 0.8 c, so 0.8 into 3 into 10 to the power 8 meter per second into this 3.33 into 10 to the power minus 8. So it will become in meter, and it will come, if you calculate, it will come 8 meter. So that's the answer. And with this we end today's video, and more part on this special theory of relativity will come, and in those part I will be discussing more complicated things. This is the first video on STR, so I have covered relatively simple things which we are already quite aware about, and in the upcoming videos I will be discussing about the other consequences of Lorentz transformation with some solved examples, and after 1 or 2 videos we'll consider the electrodynamics part also, electromagnetic field tensor and all. So stay connected, and if you like the video, please give it a thumbs up, and if you are any visitor of this channel, please subscribe the channel and don't forget to press the bell icon. Finally, thanks for watching.